In this screencast, I'm going to turn to multiple integration over non-rectangular domains, and I will begin with a region of type 1. And this is the standard kind of question you'd be asked. You're asked to evaluate this integral, double integral over of this function over a region omega, which is described as being bounded between two parabolas, this parabola and that parabola. And the first thing to note is that the question is not stated as explicitly as an integration over type 1. That's for you to figure out. And in fact, I would suggest that let's not focus too much on whether on the terminology type 1 or type 2. Your job is, from this problem description, is to work out what the geometry of omega is and think about how it is you're going to set up this this integral as a repeated integral. That's really your job. All right, and so what you're going to do, surely, is whether it's asked for or not, you better get in the habit of just sketching these regions and making sure you understand them. So let's do that. So this is x and y, as usual, and I have two parabolas. Let's do this lower one, so that's y is equal to 2x. So if this is 1 and this is 2, just helps me if I know where I'm going to hit here. Okay, not perfect, but not bad. All right, and then I have my other one, which is 1 plus x squared, so I'll start here at 1, and I'll go x squared, so that will also go through. Again, not perfect, but not too bad. So these points where they intersect, now I already knew this, but you can easily see from this, this will be 1, 2, and this point here will be minus 1, 2. And so then this is your region, this is your omega. Now at this point, you ask yourself, well, again, I wasn't told it was of a particular type. I think about how I'm going to set up an integral here, and I can see, I will go ahead and do this, you can see that you cannot integrate at constant y. You don't have a region here you can integrate across an x. All right, so it's not going to be a type 2 region, that's for sure. But you can see that anywhere, for any given value of x, I have these definite limits in y that I can integrate. I can integrate from there to there, there to there, and that's true everywhere here. And well, that's the way it is. So what I surely want to do is set up my limits of x between the range of my domain. The domain starts with x is equal to minus 1 and goes to x is equal to plus 1. So I'll set this up. And then for any given x, the range of y is, this lower boundary is y is equal to 2x squared. The upper boundary is 1 plus x squared. I want to put in y is equal to, just to be y equal 1 plus x squared. That then describes the region, and it practically tells me how to set up the limits of integration. But in this case, I'm going to go ahead and just elaborate a little bit more. I'm going to actually write down what the omega is as a set of points. Perhaps this is unnecessary in this case, but good practice here. So x will be between minus 1 and 1. What will y be between for any given x? It will be between 2x squared and 1 plus x squared. So hopefully I haven't made any mistakes thus far. All right, so once I have all of this, once I have my sketch and my visualization in my head of what this region looks like, and I've even explicitly stated out, well, then I can just write down the integral, and I'll do it over here directly. So this this double integral, didn't really need to do this. dA will be equal to the repeated integral. X is clearly on the outside, followed by y, and the limits of y depend on x, 2x squared, 1 plus x squared. Then I have my function, and then dy first, and then dx. Getting a little close here. Let's just move that up. Okay, good. So the rest is just integration, and I'll do it as quickly as possible. Just make a few points. Again, I'll go ahead and, so this is one of our early ones. So you're going to focus on this inner integral first, all right? And everywhere in there, I'll stop saying this later. Everywhere in there, x is a constant. So we just integrate x as a constant in there. So the x integral stays where it was for now. Integrate x with respect to y, so that's just xy plus 2y squared over y. And the limits now are a little bit more complicated. We have 2x squared. I'm not leaving quite enough room. And dx. All right, so now we have to substitute in, and I will go ahead and we have to substitute in these limits, which themselves depend on x, and they go everywhere that there's a y in here. with the appropriate signs. Okay, the usual substitution, but I just wanted to indicate that. That's what I'm now going to do. So let's do it. Again, this interval stays here. And then we have long thing x. Now we're going to substitute in 1 plus x squared for y plus y squared. And we're going to substitute in 1 plus x squared. Now we have to do the lower limit with the minus sign. So we have x times y. X is, so we're going to get a 2x cubed. I've done this into there with the minus sign. Now the other one, minus 4x to the 4th dx. So again, let me just emphasize, at this point when we've done all this integration, it's done with respect to y. X is treated as constant. And what happens is, even though these limits here depend on x, when I do this substitution at this stage of integral, what I will be left with here is something that this integrand now depends only on x and between constant limits. So this is the kind of integral you should be able to just whip right through. I'm going to do it by, I've pre-written it down. I've written this as a single polynomial, which I'm sure you can do very quickly. Minus 3x to the 4th minus x cubed plus 2x squared plus x plus 1 dx. And all right, let's just do it. Minus 3x to the 5th over 5. I hope I don't make any mistakes. It'll be embarrassing here. X to the 4th over 4 plus, I'm just going to say that's not going to be an x. Oh, no, it's x. No, sorry, I almost made a mistake. 2x cubed over 3 plus x squared over 2 plus 1. I did that fast. I hope I didn't make a mistake. It should be an x, obviously. All right, so minus 1 to 1. Anyway, I have written down the answer. It's 32 over 15. So you can check that, and if I made a mistake, don't worry too much. I mean, tell me, I'll correct it, but there we go. Let's not worry about that. Anyway, that's your answer, and again, that's how you do problems of this type.